Equilibrium and transient climate sensitivity. The equilibrium climate sensitivity refers to the equilibrium change in global mean near surface air temperature that would result from a sustained doubling of the atmospheric carbon dioxide concentration. As estimated by the IPCC Fifth Assessment Report, there is high confidence that ECS is extremely unlikely less than 1 degree Celsius and medium confidence that the ECS is likely between 1.5 degrees Celsius and 4.5 degrees Celsius and very unlikely greater than 6 degrees Celsius. Quote, "This is a change from the IPCC Fourth Assessment Report, which said it was likely to be in the range 2 to 4.5 degrees Celsius with a best estimate of about 3 degrees Celsius, and is very unlikely to be less than 1.5 degrees Celsius. The values substantially higher than 4.5 degrees Celsius cannot be excluded, but agreement of models with observations is not as good for those values." The IPCC Third Assessment Report said it was likely to be in the range of 1.5 to 4.5 degrees Celsius. Other estimates of climate sensitivity are discussed later on. A model estimate of equilibrium sensitivity thus requires a very long model integration. Fully equilibrating ocean temperatures requires integrations of thousands of model years. A measure requiring shorter integrations is the transient climate response, which is defined as the average temperature response over a 20-year period centered at CO2 doubling in a transient simulation with CO2 increasing at 1% per year. The transient response is lower than the equilibrium sensitivity due to the inertia of ocean heat uptake. Over the 50 to 100-year timescale, the climate response to forcing is likely to follow the TCR. For considerations of climate stabilization, the ECS is more useful. An estimate of the equilibrium climate sensitivity may be made from combining the transient climate sensitivity with the known properties of the ocean reservoirs and the surface heat fluxes. This is the effective climate sensitivity. This may vary with forcing history and climate state. A less commonly used concept, the Earth system sensitivity, can be defined, which includes the effects of slower feedbacks, such as the albedo change from melting the large ice sheets that covered much of the northern hemisphere during the last glacial maximum. These extra feedbacks make the airs larger than the ECS, possibly twice as large, but also mean that it may well not apply to current conditions. Sensitivity to carbon dioxide forcing. Climate sensitivity is often evaluated in terms of the change in equilibrium temperature due to radiative forcing due to the greenhouse effect. According to the Arrhenius relation, the radiative forcing is proportional to the logarithm of the concentration of infrared-absorbing gases in the atmosphere. Thus, the sensitivity of temperature to gases in the atmosphere is often expressed in terms of the change in temperature per doubling of the concentration of the gas. CO2 climate sensitivity has a component directly due to radiative forcing by CO2, and a further contribution arising from climate feedbacks, both positive and negative. Without any feedbacks, a doubling of CO2 would result in 1 degree Celsius global warming, which is easy to calculate and is undisputed. The remaining uncertainty is due entirely to feedbacks in the system, namely, the water vapor feedback, the ice albedo feedback, the cloud feedback, and the lapse rate feedback. Addition of these feedbacks leads to a value of the sensitivity to CO2 doubling of approximately 3 degrees Celsius plus or minus 1.5 degrees Celsius, which corresponds to a value of lambda of 0.8 K. In the earlier 1979 NAS report, the radiative forcing due to doubled CO2 is estimated to be 4 W per square meter, as calculated in Ramanathan et al. In 2001, the IPCC adopted the revised value of 3.7 W per square meter, the difference attributed to its stratospheric temperature adjustment. More recently, an intercomparison of radiative transfer codes showed discrepancies among climate models and between climate models and more exact radiation codes in the forcing attributed to doubled CO2 even in cloud-free sky. Presumably the differences would be even greater if forcing were evaluated in the presence of clouds because of differences in the treatment of clouds in different models. Undoubtedly, the difference in forcing attributed to doubled CO2 in different climate models contributes to differences in apparent sensitivities of the models, although this effect is thought to be small relative to the intrinsic differences in sensitivities of the models themselves. Consensus estimates. A committee on anthropogenic global warming convened in 1979 by the National Academy of Sciences and chaired by Jules Charny estimated climate sensitivity to be 3 degrees Celsius, plus or minus 1.5 degrees Celsius. Only 2 sets of models were available. One, due to Sukuro Manabe, exhibited a climate sensitivity of 2 degrees Celsius. The other, due to James E. Hansen, exhibited a climate sensitivity of 4 degrees Celsius. According to Manabe, Charny chose 0.5 degrees Celsius as a not unreasonable margin of error, subtracted it from Manabe's number, and added it to Hansen's. Thus was born the 1.5 degrees Celsius to 4.5 degrees Celsius range of likely climate sensitivity that has appeared in every greenhouse assessment since. Chapter 4 of the Charny report compares the predictions of the models. We conclude that the predictions are basically consistent and mutually supporting. The differences in model results are relatively small and may be accounted for by differences in model characteristics and simplifying assumptions. In 2008, climatologist Stefan Rahmstorff wrote regarding the Charny report's original range of uncertainty. At the time, this range was on very shaky ground. Since then, many vastly improved models have been developed by a number of climate research centers around the world. Current state-of-the-art climate models span a range of 2.6 to 4.1 degrees Celsius, most clustering around 3 degrees Celsius. Intergovernmental Panel on Climate Change. The 1990 IPCC First Assessment Report estimated that equilibrium climate sensitivity to CO2 doubling lay between 1.5 and 4.5 degrees Celsius, with a best guess in the light of current knowledge of 2.5 degrees Celsius. This used models with strongly simplified representations of the ocean dynamics. The IPCC Supplementary Report, 1992, which used full ocean GCMs, nonetheless saw no compelling reason to warrant changing from this estimate, and the IPCC Second Assessment Report found that no strong reasons have emerged to change these estimates, with much of the uncertainty attributed to cloud processes. As noted above, the IPCC TAR retained the likely range 1.5 to 4.5 degrees Celsius. Authors of the IPCC Fourth Assessment Report stated that confidence in estimates of equilibrium climate sensitivity had increased substantially since the TAR. AR4's assessment was based on a combination of several independent lines of evidence, including observed climate change in the strength of known feedbacks simulated in general circulation models. IPCC authors concluded that the global mean equilibrium warming for doubling CO2, or equilibrium climate sensitivity, very likely is greater than 1.5 degrees Celsius. Celsius and likely to lie in the range 2 to 4.5 degrees Celsius, with a most likely value of about 3 degrees Celsius. For fundamental physical reasons, as well as data limitations, the IPCC states a climate sensitivity higher than 4.5 degrees Celsius cannot be ruled out, but that agreement for these values with observations and proxy climate data is generally worse compared to values in the 2 to 4.5 degrees Celsius range. The TAR uses the word likely in a qualitative sense to describe the likelihood of the 1.5 to 4.5 degrees Celsius range being correct. AR4, however, quantifies the probable range of climate sensitivity estimates. 2 to 4.5 degrees Celsius is likely, equals greater than 66% chance of being correct. Less than 1.5 degrees Celsius is very unlikely, equals less than 10%. The IPCC Fifth Assessment Report stated, equilibrium climate sensitivity is likely in the range 1.5 degrees Celsius to 4.5 degrees Celsius, extremely unlikely less than 1 degree Celsius, and very unlikely greater than 6 degrees Celsius. These are Bayesian probabilities, which are based on an expert assessment of the available evidence. Calculations of CO2 sensitivity from observational data. Sample calculation using industrial-age data. Rahmstorff provides an informal example of how climate sensitivity might be estimated empirically, from which the following is modified. Denote the sensitivity, i.e., the equilibrium increase in global mean temperature including the effects of feedbacks due to a sustained forcing by doubled CO2, as x degrees C. If Earth were to experience an equilibrium temperature change of delta T due to a sustained forcing of delta F, then one might say that x equals i.e., that x equals delta T asterisk delta F. The global temperature increase since the beginning of the industrial period is about 0.8 degrees Celsius, and the radiative forcing due to CO2 and other long-lived greenhouse gases emitted since that time is about 2.6 W per square meter. Neglecting other forcings, and considering the temperature increase to be an equilibrium increase would lead to a sensitivity of about 1.1 degrees Celsius. However, delta F also contains contributions due to solar activity, aerosols, ozone and other lesser influences, bringing the total forcing over the industrial period to 1.6 W per square meter according to best estimate of the IPCC AR4, albeit with substantial uncertainty. Additionally, the fact that the climate system is not at equilibrium must be accounted for. This is done by subtracting the planetary heat uptake rate h from the forcing i.e. x equals delta T asterisk. Taking planetary heat uptake rate is the rate of ocean heat uptake, estimated by the IPCC AR4 as 0.2 W per square meter, yields a value for x of 2.1 degrees Celsius. Sample calculation using Ice Age data in 2008. Farley wrote, examine the change in temperature and solar forcing between glaciation and interglacial periods. The change in temperature, revealed in ice core samples, is 5 degrees Celsius, while the change in solar forcing is 7.1 W per square meter. The computed climate sensitivity is therefore 5/7.1 equals 0.7 K-1. We can use this empirically derived climate sensitivity to predict the temperature rise from a forcing of 4 W per square meter, arising from a doubling of the atmospheric CO2 from pre-industrial levels. The result is a predicted temperature increase of 3 degrees Celsius, based on analysis of uncertainties in total forcing, in Antarctic cooling, and in the ratio of global to Antarctic cooling of the last glacial maximum relative to the present. Gonopolsky and Schneider von Deimling infer a range of 1.3 to 6.8 degrees Celsius for climate sensitivity determined by this approach. A lower figure was calculated in a 2011 science paper by Schmittner et al., who combined temperature reconstructions of the last glacial maximum with climate model simulations to suggest a rate of global warming from doubling of atmospheric carbon dioxide of a median of 2.3 degrees Celsius and uncertainty 1.7 to 2.6 degrees Celsius, less than the earlier estimates of 2 to 4.5 degrees Celsius as the 66% probability range. Schmittner et al. Said their results imply less probability of extreme climatic change than previously thought. Quote, "The work suggests that climate sensitivities and GT 6 degrees Celsius cannot be reconciled with paleoclimatic and geologic evidence, and hence should be assigned near zero probability." Other experimental estimates, IDSO calculated based on 8 natural experiments, a lambda of 0.1 degrees Celsius, resulting in a climate sensitivity of only 0.4 degrees Celsius for a doubling of the concentration of CO2 in the atmosphere. Andronova and Schlesinger found that the climate sensitivity could lie between 1 and 10 degrees Celsius, with a 54% likelihood that it lies outside the IPCC range. The exact range depends on which factors are most important during the instrumental period. At present, the most likely scenario is one that includes anthropogenic sulfate aerosol forcing but not solar variation, although the value of the climate sensitivity in that case is most uncertain. There is a 70% chance that it exceeds the maximum IPCC value. This is not good news, said Schlesinger. Forrest et al., using patterns of change in the MIT estimated a 95% confidence interval of 1.4 to 7.7 degrees Celsius for the climate sensitivity, and of 30% probability that sensitivity was outside the 1.5 to 4.5 degrees Celsius range. Gregory et al. Estimated a lower bound of 1.6 degrees Celsius by estimating the change in Earth's radiation budget and comparing it to the global warming observed over the 20th century. Shaviv carried out a similar analysis for 6 different time scales, ranging from the 11-year solar cycle to the climate variations over geological time scales. He found a typical sensitivity of 0.54 plus or minus 0.12 K, or 2.1 degrees Celsius if there is no cosmic ray climate connection, or a typical sensitivity of 0.35 plus or minus 0.09 K, or 1.3 degrees Celsius, if the cosmic ray climate link is real. Frame et al. Noted that the range of the confidence limits is dependent on the nature of the prior assumptions made. Annan and Hargreaves presented an estimate that resulted from combining prior estimates based on analyses of paleoclimate, responses to volcanic eruptions, and the temperature change in response to forcings over the 20th century. They also introduced a triad notation to convey the probability distribution function of the sensitivity, where the central value C indicates the maximum likelihood estimate in degrees Celsius and the outer values L and H represent the limits of the 95% confidence interval for a PDE, or 95% of the area under the curve for a likelihood function. In this notation their estimate of sensitivity was degree C. Forster and Gregory presented a new independent estimate based on the slope of a plot of calculated greenhouse gas forcing minus stop of atmosphere energy imbalance, as measured by satellite-borne radiometers, versus global mean surface temperature. In the triad notation of Annan and Hargreaves their estimate of sensitivity was degree C. Royer et al. Determined climate sensitivity within a major part of the Phanerozoic. The range of values 1.5 degrees Celsius minimum, 2.8 degrees Celsius best estimate, and 6.2 degrees Celsius maximum bullshit, given various uncertainties, consistent with sensitivities of current climate models and with other determinations. Lindzen and Choi find the equilibrium climate sensitivity to be 0.7 C, implying a negative feedback of clouds. Skay et al. Use the Bayesian analysis of the OHC data and conclude that the equilibrium climate sensitivity is 1.8 C, far lower than previous best estimate relied upon by the IPCC. Aldrin et al. Use a simple deterministic climate model, modeling yearly hemispheric surface temperature and global ocean heat content as a function of historical radiative forcing, and combine it with an empirical, stochastic model. By using a Bayesian framework they estimate the equilibrium climate sensitivity to be 1.98 C. Lewis estimates by using the Bayesian framework that the equilibrium climate sensitivity is 1.6 K, with the likely range 1.2 to 2.2 K. Science Daily reported on a study by Faslow and Trenber, who tested model estimates of climate sensitivity based on their ability to reproduce observed relative humidity in the tropics and subtropics. The best performing models tended to project relatively high climate sensitivities of around 4 degrees Celsius. Previdi et al. 2013 reviewed the 2 times CO2 Earth system sensitivity, and concluded it is higher if the ice sheet and the vegetation albedo feedback is included, in addition to the fast feedbacks being 4 to 6 degrees Celsius, and higher still if climate GHG feedbacks are also included. Lewis and Curry estimated that equilibrium climate sensitivity was 1.64 degrees Celsius, based on the 1750 to 2011 time series and the uncertainty ranges for forcing components in the IPCC's Fifth Assessment Report. Literature reviews. A literature review by Nutty and Hagel concluded that various observations favor a climate sensitivity value of about 3 degrees Celsius, with a likely range of about 2 to 4.5 degrees Celsius. However, the physics of the response and uncertainties in forcing lead to difficulties in ruling out higher values. Radiative forcing functions. A number of different inputs can give rise to radiative forcing, in addition to the downwelling radiation due to the greenhouse effect. The IPCC First Scientific Assessment Report listed solar radiation variability due to orbital changes, variability due to changes in solar irradiance, direct aerosol effect, indirect aerosol effect, and surface characteristics. Sensitivity to solar forcing. Solar irradiance is about 0.9 W per square meter brighter during solar maximum than during solar minimum. Analysis by Camp and Tung shows that this correlates with a variation of plus or minus 0.1 degrees Celsius in measured average global temperature between the peak and minimum of the 11-year solar cycle. For this data, Tung, Zhou and Camp derive a transient sensitivity value of 0.69 to 0.97 degrees Celsius. This would correspond to a transient climate sensitivity to carbon dioxide doubling of 2.5 to 3.6 K, similar to the range of the current scientific consensus. However, they note that this is the transient response to a forcing with an 11-year cycle, due to lag effects. They estimate the equilibrium response to forcing would be about 1.5 times as high.